this unit, we explore exponential functions, which are used to model rapid growth and decay in the real world. From money in a bank account to how medicines leave the body, exponential relationships help us understand change over time. By the end of this unit, you will be able to read, graph, and analyze exponential functions with confidence. Some situations grow slowly, while others grow faster and faster. Exponential relationships can help us describe patterns where values change by multiplying instead of adding, which happens often in science, finance, and technology. Relationship. A relationship shows how one quantity changes when another quantity changes. As time increases, the amount of money in a savings account changes. Exponent. An exponent tells us how many times a number is multiplied by itself. In 2 to the 5th power, the exponent 5 means 2 is multiplied by itself 5 times. Exponential. A value changes by multiplying by the same number each time. If a value doubles every hour, it is changing exponentially. Arithmetic sequence. A sequence that increases or decreases by adding the same amount each time. The sequence, 2, 5, 8, and 11, adds 3 each step, so it is arithmetic. Exponential growth. Exponential growth happens when values increase faster and faster over time. A population that doubles every year shows exponential growth. Exponential decay. Exponential decay happens when values decrease by 1% over time. A phone battery losing 10% of its charge each hour shows decay. Half-life. The time it takes for a quantity to decrease to half its value. If a medicine has a half-life of 6 hours, half remains after 6 hours. Graphs help us see how exponential functions behave. By learning their features, we can quickly understand what a graph is telling us. Parent function. The simplest form of a function. The parent function for an exponential is y equals 2 to the x. Base graph. The original graph before any changes are made. The graph of y equals 3 to the x is a base graph. Function notation. A way to write a function that shows how input values turn into output values. For example, in f of x equals 2 to the x is the input. Domain. All the possible x values a function can use. Exponential functions can use any real x value. Range. All of the possible y values a function can produce. The base exponential graph stays above 0, so y is always positive. Intercept. Where a graph crosses an axis. The x-intercept is where the graph crosses the x-axis, while the y-intercept is where it crosses the y-axis. Zero of an exponential function. Where a graph crosses the x-axis, meaning f of x equals 0. Unless the graph has a vertical shift, an exponential function does not usually cross the x-axis. Characteristics of a graph. These are important features of a graph. This includes intercepts, shape, and direction. Looking at how a graph moves helps us predict what will happen in the future. This is useful when modeling money, populations, and technology growth. Strictly increasing. A graph is strictly increasing if it always goes up as x increases. The graph of exponential growth is strictly increasing. Strictly decreasing. A graph is strictly decreasing if it always goes down as x increases. Exponential decay graphs are strictly decreasing. Interval of increase. The part of a graph where the graph goes up. An exponential growth function increases for all x values. Interval of decrease. The part of a graph where the graph goes down. Exponential decay decreases for all x values. End behavior. What happens to the graph as x becomes very large or very small? For example, as x increases, exponential growth rises quickly. Some graphs never stop growing or shrinking. Infinity helps us describe what is happening as values move beyond what we can see. Infinity, something that continues without end. For example, this graph keeps rising towards infinity. Positive infinity, values that grow larger and larger. As x increases, y moves towards positive infinity. Negative infinity, values that get smaller without stopping. As x decreases, y moves towards negative infinity. Asymptote, a line that a graph gets closer and closer to but never touches. As the graph keeps going, it moves towards this line without ever reaching it. This line helps us understand how the graph behaves as it goes on forever. Asymptotic behavior. Asymptotic behavior means the graph gets closer and closer to a line but never touches it. The x-axis is a horizontal asymptote for many exponential graphs. Transformations change how a graph looks without changing its overall shape. These shifts help us model real-world situations more accurately. Transformation. Transformations are changes made to a graph's position or size. Moving a graph up or down is a transformation. Vertical translation. Moving a graph up or down. Adding 3 moves the graph up 3 units. For example, y equals 2 to the x power plus 3. Horizontal translation. Moving the graph left or right. Subtracting 2 inside the function moves it right, like y equals 2 raised to the quantity x minus 2 power. Stretch. A stretch makes the graph taller or wider. Multiplying the function by 2 stretches it upwards, like y equals 2 times 2 to the x power. Compression. A compression makes the graph shorter or narrower. Multiplying by 0.5 compresses the graph, like y equals 0.5 times 2 to the x power. Exponential functions are everywhere in real life, especially when money or science is involved. Understanding these models helps you make smarter decisions. Simple interest. A type of interest that earns the same amount of money each time period. For example, a savings account where you earn $10 each year on a $100 investment. Compound interest. A type of interest that earns interest on both the money and the past interest. It is usually calculated 1 or more times per year.